Some people think diodes are easier than op amps. Some people think diodes are not easier than op amps. You would think the simplicity of the device would make them easier, but the sheer volume of applications makes it a little bit more detailed than op amps. The nice thing about op amp circuits is technically there's only two, and when you figure out the two, then you just put them together into bigger circuits, and diodes aren't quite that simple. There's a lot of stuff we can do with them. So this week we're just talking about what they're made out of and how to use ideal diodes in circuits. And we'll talk about the difference between ideal diodes and constant voltage drop diodes and actual diodes. There's like 3 different ways we can think about them. But this week we're mostly going to think about them in the ideal fashion, which I don't know if it makes it really easier, but it can be useful in general. They are cooler than like insulators, and they are cooler than conductors. Reason why. First of all, resistivity. Resistivity is not the entire thing that determines resistance, but it is a material-based metric that can basically tell you what the resistance is going to be given a certain length and cross-sectional area. So, first of all, insulators have very, very, very high resistivities. Quartz, sulfur, diamonds, glass, all of those things are good insulators because resistivity is high, so the resistance is high, so you just can't get any current to go through them. On the other end, conductors like silver and copper and all the sort of common conductors we use, they have very, very low resistivities, really, really, really small. So that means that they do have a resistance, but not a really big one. Long strands of wire do have a resistance, and you do have to consider it if you're running like hundreds of feet of wire, then you actually do have a significant resistance. But for the most part, we don't worry so much about that. But you'll notice with both conductors and insulators, it's a very specific resistivity that is assigned to each material. Each material has just a resistivity, and that does not change. The cool thing about semiconductors is each one and each type, and this is not an exclusive or I guess the exhaustive is the term. That is not an exhaustive list of semiconductor materials, but you will notice that each one of them has a range of resistivities, and they're intermediate between being conductors and insulators. And this is really what makes semiconductors different, is they can be designed to have a specific resistivity. They don't have to have just a specific value. And that's really what makes them useful. That's why they are used in so many things, because they can be specifically created to have a particular resistivity, which can cause it to be useful in different areas. So that's as much as I'm going to say about that part of it. We make them mostly, we can make them out of one material or combinations. There can actually be a large number of, there can be like 3 or 4 even. But the elemental types that we use, where we use just one material, are generally silicon and germanium. Silicon is by far more common than germanium. Germanium is more expensive to get. And actually, germanium diodes are difficult to find, like real ones. It's actually a whole big thing. If you want to find a germanium diode, there are tons and tons of fake germanium diodes out there because germanium is more expensive, and there can be devices manufactured to mimic germanium. And when I was working, I used to work as an adjunct at Chattahoochee Tech as well as here, and they ordered like a big bag of germanium diodes from a known supplier. So not like some fly-by-night website. It was like the one that we get catalogs for. And so she was talking to me, the lady who had ordered them, and they really didn't know anything about semiconductor devices. That's one of the reasons I was there, to do the electronics courses. And she said, well, we went through and we were checking these germanium diodes, and they have a forward voltage of like 0.68. And I said, no, you can't have that with germanium. Germanium has a forward voltage of about 0.3. And she said, well, we checked them, and that's what they came out. So that's just what I'm going to tell the students. Like, no, you can't do that. They aren't real. And they kind of didn't understand, didn't believe me. And I brought one of them over here and put it in a curve tracer, which they didn't have over there. And it didn't even look like a diode at all. It had a completely weird curve, and we determined that we couldn't even figure out what they were. Elemental semiconductors made of one material, most of the time it's silicon, and in fact in here just about all the time it's going to be silicon. You can also make them out of compounds to the left and the right of silicon or germanium, the column. Gallium arsenide is a really, really common combination of atoms that can also make up semiconductor devices. And then there are more. There are plenty more. You can make lots and lots and lots of combinations. We don't use carbon as semiconductor material necessarily, and part of the reason that we don't, from what I remember, is that getting impurities into them is difficult. It's more difficult than with silicon or germanium, and you have to have impurities to make them work properly. Actually, there is a carbon-based device that contains boron, and you'll notice that's well, for me it's to the left. I guess it's to the left for you too. I'm really bad with right and left. But there is a very famous carbon device that is doped with boron or has boron impurities, and it's the Hope diamond. The Hope diamond is blue, and the reason it's blue is because it has boron mixed with the carbon that made the crystal that made the diamond. So that's like not at all related to anything that we're doing actually in here, but it's just an interesting factoid that, you may someday need to know that. The resistance of any semiconductor material depends on the resistivity and then how long it is and the cross-sectional area. So for pure semiconductor material, there is a specific resistivity for that pure material. However, the resistivity can be changed by adding different impurities. That's how we basically make them have a wide range of resistivities, is by adding impurities that will cause the resistivity to change. So pure, undoped, or without impurity semiconductor is called intrinsic. So that's what an intrinsic semiconductor material would be like, just germanium or just silicon by itself with nothing added, or even gallium arsenide with nothing else different added. A doped semiconductor material is called extrinsic. That has some types of impurities in it. Intrinsic semiconductor material actually forms a crystal structure that's really stable. This is one of the reasons why it's used, because it makes a very stable structure. You know that diamond makes a really stable structure. It has to have a lot of pressure to make it. Otherwise, it forms graphite. If there's not enough pressure, you get graphite. If you get a whole lot of pressure, you get diamond. Making a single crystal of a semiconductor material is not all that difficult. It basically is done by taking a seed of pure semiconductor material and putting it in a big melting pot and kind of pulling it out, and it creates a strand, and depending on how you rotate the big melt, you get a bigger and bigger they're huge. They're like 6 feet long and this big around. The ingot, yeah. And actually, the way that they're made, the original method was discovered completely by accident by this dude about 100 years ago who was working with tin, which is also in the same area of semiconductor material, and he was writing down his thoughts, and he dipped his pen into the tin instead of his inkwell. And when he pulled the pen out, he had this strand of tin, and when he checked it, he found it was like a single crystal of tin. And that's kind of how the method started. It's called the Czochralski method, and it actually was just discovered by accident, still used today as one of the ways that semiconductor material is made. Not the only way, but one of them. So you just never know what you might discover by accident. You know, nobody uses inkwells anymore, but you just never know. A lot of stuff like that is just discovered by happenstance. So the atoms in silicon or germanium or other semiconductor material bond covalently. That means that they share electrons between each other. Each one of the materials that is used, usually if I'm talking about silicon, has an outer valence shell with 4 electrons. In order to reduce the energy as much as possible, each one of the atoms wants 8. And if they share them amongst each other, then you'll see that they actually, when I get to that point, they actually can look like they have 8 around each atom when they really don't. So the charge carriers in semiconductor material are either free electrons, and free electrons are ones that have a positive energy and are not bound to the nucleus, or holes. And holes are actually spaces in the bonding structure that electrons have left to go on to better things, and they have left a hole behind. And the way it works is it's still electrons moving that makes these holes move because they're gaps. And basically just one electron falls into another hole and leaves a hole behind, and so the holes kind of move, even though it's really electrons that are doing the motion. It's just a different motion than they have when they are free electrons. So at absolute zero, if you have any kind of semiconductor material, if you make it as cold as it can be in the whole universe, nothing will happen. All of the electrons are just sitting there, bound up, and they have no energy to go anywhere. But as temperature goes up, more and more electrons gain enough energy to be freed from the bonding structure, and they create electrons and holes. So this is what silicon looks like as a structure. And you'll notice that each one of these is sharing electrons so that it looks like each atom has 8 around it. In reality, each one is providing 4, and they're just kind of sharing the electrons between them. And if an electron gains enough energy, it kind of just flies off into the conduction band, and it leaves a hole behind. You like that? That was fun to do. Just flies off, yeah. But that's basically what it does. It becomes unbound, and then it becomes free to move. It does not move generally in a trajectory, though. Actually, what it does is kind of do this kind of drifty thing until you provide a voltage, and then that will give it some direction. It needs some direction before it will actually work. So as the temperature of intrinsic silicon goes up, electrons and holes are created in pairs, because anytime an electron leaves the bond, it produces a hole. So you have the same number of electrons as holes. And since the numbers are equal, you can get some current to flow, but making an imbalance makes it work better. So creating a situation in which there are more electrons than holes, or more holes than electrons, actually gives material variable resistivity and the ability to do more than it would intrinsically. So there are 2 kinds of semiconductor materials that you get when you add impurities. You either get N-type material, and that's when you add something that makes more electrons available, and that means that it's still not a charged thing, because when you add your impurities, the impurities still have the same number of protons and electrons in each atom. So it's not adding electrons to give it charge, it's just adding electrons to make more electrons available to carry a charge. P-type material is doped so that there are more holes available than electrons. And it's still, again, charge neutral, but the actual extra holes make it easier to conduct electricity. So, with N-type material, you can add antimony, which is just to the right. I think it's to the right. To the right. Again, my rights and lefts are not very good. So when antimony is added, there's an extra electron kind of hanging out there. And it's not as tightly bound to its own nucleus because there's already kind of a full valence shell there. So that extra electron is just kind of like literally a fifth wheel. And it is easier to gain enough energy for this electron to go off into the conduction energy level than it would be for one that would be bound. So they tend to kind of float off really easily, easier than the electrons that are in the original structure. And they don't leave a hole behind. And that's the key. There's an electron available, it goes and becomes available for conduction of electricity, but doesn't create another hole in the process. So that is what you do when you get N-type material. P-type material, you actually, boron is a good example. We're actually adding something that lacks an electron. So when it is part of the structure, there's actually a hole already there. And the way these holes move is not by obviously flying off into space, because they can't. But the way they move is adjacent electrons kind of move into the space. So that electron might move over, and then one from the other silicon might move over, and the hole is actually technically moving in a particular direction. So the weird thing about holes is they are actually caused by electron movement, but the electron movement is completely different than the electron movement that the electrons that are free make. So that sort of makes them a different type of charge carrier. So once we get semiconductor material in N-type or P-type, there are electrons and holes in both kinds, because the ones that are made in intrinsic material are still made. They're still there. So there is, in N-type material, there are holes, but there are more electrons. So we say that electrons are the majority charge carriers and holes are the minority charge carriers. They're still there, there are just less of them. In P-type material, there are more holes than electrons, so the hole is the majority charge carrier and the electrons are the minority carrier. And this, when you get into devices where you're starting to put N-types and P-types together, both of the charge carriers actually have a role in how these particular devices work. So now that we've got that, we've got sort of N-type and P-type material. Once we do that, we're going to make a device. And the device, the first thing we're going to use in here is going to be a diode. And a diode, most diodes, not all diodes, but is just P material and N material next to each other. So when we have, and this is not a very good representation, it's kind of an illustration, but let's say we have P material, and you'll notice there are more holes than electrons on that side, and N material, where there are more electrons than holes. And they are manufactured together, not stuck together, but they're actually manufactured together. But our assumption, and this is a reasonably good assumption, is that the junction in which they meet is a pretty sharp divide. So the P material goes right up to a point, the N material is on the other side, and at that junction, stuff happens. Because on one side, you've got more electrons. On the other side, you've got more holes. And what ends up happening is right at that junction, some of the electrons and some of the holes recombine because they're right next to each other. And when that happens, that actually creates an area that has no charge carriers but does have an electric field. So it does have a polarity. And this is known as the depletion region. In the depletion region, there's actually a barrier to charges moving because it's polarized. So, and this all, I think this is the coolest thing about semiconductors, this all happens inside a device that's just sitting like on a table, not doing anything. So this field inside of here is created just by the fact that it's sitting at room temperature, not connected to anything. So once this depletion region is in play, there aren't any charge carriers in that particular area. And because it's polarized and there's a positive charge on the N side and a negative charge on the P side, eventually it stops growing. It comes to kind of an equilibrium point, and it just stays there. So that area of depletion right at the junction is just there inside the device. And the width of that region depends on the doping concentrations of the P side and the N side. So that's another thing one does in semiconductor devices. You figure out how wide the width is, and the more lightly doped, the farther the depletion region goes into that side. And that's just, you can create them all kinds of different ways. So what happens when we actually use a device like this? So the first thing that we talk about, there's a term that we use, and we use this not only with diodes, but we use it with MOSFETs, we use it with BJTs. It's a term called bias. And bias is just a DC voltage that's applied to something that creates within it certain conditions. So a zero bias PN junction, which is just a diode sitting on a table, not connected to anything, it has no voltage across it. It has no current going through it, obviously. And there may be charges that are drifting back and forth across that depletion region because there is still stuff going on, but it's not going to do anything. So it just sits there. It has a depletion region. There is no voltage, and that's basically what we see with that. That's not very interesting. So if we apply a voltage to this, we can apply a voltage in one of two directions. We can polarize it one way, we can polarize it the other way, basically. We have two choices. So the first way we're going to do it is something known as reverse bias. We're actually going to apply a voltage that will enhance this depletion region. So reverse bias means that the voltage across the diode is less than zero, and there's actually a certain polarity it has to follow. So it has to have the positive on the N side, the negative on the P side. And when that happens and the voltage is applied, basically the depletion region gets enhanced. So the positive on the N side, the negative on the P side actually makes that depletion region grow, which makes it even harder for current to flow. So it makes it so that really current doesn't flow. There is a very, very, very tiny amount of current that is composed of minority charges that actually does flow, but it's really small. It's known as the saturation current, IS, and it's tiny. It's, times 10 to the minus 9 or 12 amps, something like that. Really small. So that does always occur, but it's not anything that's going to affect a circuit very much. So that's one way. That's a reverse bias. That's basically a DC voltage that's applied that makes the ability to pass charge for a diode even worse than what it was initially. The other way we can do it is a forward bias. In a forward bias, we apply a voltage that actually pushes the depletion region to be narrower. So we get a positive on the P side and a negative on the N side, and that basically causes that depletion region to shrink. And once this small voltage in the middle, there's actually a voltage across that depletion region, which is kind of like a barrier or a threshold voltage. Once that voltage is crossed, current just flows, and it flows at a rate determined by the rest of the circuit, which is why you don't ever connect a diode to a power supply without a resistor, because that will basically just pull whatever current you can get out of your power supply and will blow up the diode and or the power supply, depending. So once you get this depletion region eliminated, The current that flows through it is usually on the order of milliamps, depending on the kind of diode you're using, and the current will flow fairly freely. So those are the two ways that you can connect a two-terminal diode device. The way the current is calculated, the forward bias current, is not linear. So unlike resistors, capacitors, and inductors, those things, yes, those are linear devices. Basically, there is a linear relationship between the voltage and the current, even if you have to take integrals or derivatives in the case of inductors and capacitors. There's still a linear relationship between what the impedance of those is and the voltage and the current. With diodes, it is not a linear relationship. The diode current depends on several things. A lot of them are environmental or based on the material you make the diode from. So the reverse saturation current, the one that I talked about, that figures into the forward current also, because it is also a current that is going to flow no matter what the polarity of the voltage is. And then you have the exponential function E raised to the whatever the voltage across the diode is, divided by eta. And eta is a number that is associated with the material that you use. Between 1 and 2 can be calculated. We generally assume that it's 1 in here to make things easier. So for any kind of, depending on what kind of diode you're using, it is possible to get the characteristics of the diode and figure out what the value of N is, or eta. You use either N or eta, so you might see it as an N or an eta, but either one of those, usually 1 is a good number to use in here when we're talking about actual devices. And then VT is the thermal voltage. It's something that if you've taken semiconductor devices, we calculate KT over Q quite frequently, and that's all that is. It's just in this class, we always assume we're functioning at room temperature, so we never have to change that, so it's kind of a constant. And also, there are two kind of ways to make assumptions about room temperature. You can either assume it's 300 K, which is a great, nice round number, and we use that in semiconductor devices all the time because it's a great, nice round number, and all the other constants for semiconductors are done at 300 K. But in reality, 273 is a better approximation, and that's why we get 25 millivolts for the value here, and we get more like 26 in semiconductor devices. It just has to do with the assumption we make about the Kelvin value of temperature in the room. So don't get tripped up. If it's 25 or 26, it doesn't really matter. It's not going to change things radically, but a lot of times we end up using 25 in here because it's a nicer number than 26. But the thermal voltage is pretty much always going to be a constant in here, yes.
And VD is the voltage that's being applied to the diode?
That is the voltage across the diode, yes. Yeah, that is the voltage across the diode. So that is basically what relates the current and the voltage. So we can actually plot that, and when we do, this is a highly idealized plot, but when we plot that, you'll see that there really isn't any current flowing through the diode in the forward bias direction until you reach this kind of 0.5 or so volts, and then it overcomes it really fast. And usually the built-in barrier voltage for silicon is about 0.7, 0.6 volts, something like that. So that voltage is what's overcoming the barrier inside the diode. So that small amount of voltage is needed, and once you get past that, then current will just flow depending on what the rest of the circuit is doing. So the resistance of the rest of the circuit is going to determine what the current is. And you'll notice that if you were to take a tangent line to this and take the rise over the run, that would give you the conductivity. It would give you 1 over the resistance. So you'll notice the resistance changes depending on the voltage and the current. It's really, really low once you get sort of past that initial voltage that needs to be dropped, but it's really high initially. So this is one of the things about semiconductor devices that makes them different, is the resistance changes, which is why it's nonlinear. So on the right is kind of a determination of what happens when you forward bias. On the left is the reverse bias, and that's completely a different scale than what's on the right. You'll notice what's on the right, the voltage goes up to 0.7, and to the left, it goes up to minus VB, which is actually tens or hundreds of volts. So you assume that the scale is compressed on the left-hand side of the horizontal axis, and it's expanded considerably in the negative vertical axis because IS is really, 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 really tiny. It's generally, like I said, in the picoamp or nanoamp range. So that current flows reverse until you get to a voltage, and the voltage that you get to, depending on the device, will actually cause current to flow massively. And that's known as the breakdown voltage. For silicon diodes, normal silicon diodes, depending on the type, it could be 50 volts, it could be 100 volts. It's usually listed in the spec sheet about what reverse voltage you need to break it down. Or you can have devices that are actually designed to do this. You can have Zener diodes, and Zener diodes are designed to cause current to flow at a specific voltage. And usually that voltage is 5 volts, 12 volts, whatever. Yes, and I'm actually talking ahead of myself. One thing to notice is that the forward bias voltage, since we're assuming we're running at room temperature, if the ambient temperature goes up, the forward voltage needed to overcome the barrier is less and less and less. So if it's going to be in a situation where the temperature is going to vary widely, then one has to take into account the fact that the barrier voltage will change depending on the conditions of the diode. Yes?
So when you have devices that range anywhere from like 40 to 60 degrees Celsius, like they change that much, how do you typically construct it?
Well,
Because that's a huge range.
you do, but you notice that the change is only 2 millivolts or something. So it's not a huge difference, but there are, depending on the type of device, you can actually find devices that won't be so temperature sensitive. So you basically have to choose the device properly. So in the reverse direction, there are 2 mechanisms that actually make current flow. One of them is just the breakdown voltage, and that is a bad thing. If you get your diode to where it has broken down, what happens is the current flowing through it becomes instantaneously too high, and then you get heat, and from heat you get more charge carriers, and from that you get more current, and from the current you get more heat, and that's basically known as avalanche breakdown, and it burns up the diode. So it's a bad thing. And you smell the diode, yes. That smells bad. Zener diodes have a smaller breakdown voltage and a different mechanism for how they work. So they do not, I'll get to you in a second, they do not use this avalanching thing in order to conduct current. They actually are designed such that charges can tunnel through this barrier and allow current to flow without damage. So they can repeatedly be used in that way. So that's basically all I'm going to tell you about materials and such that go into making diodes.